All right, so let's good. So the MD log is or the metadata journal for the MDS is the primary holder of all metadata mutations that the MDS makes as it goes. So any change that needs to be durable that the MDS makes will end up in the MDS journal with a little asterisk next to that. We'll get into it later. Some of the things the journal contains are some of the recent metadata mutations. So that's the obvious stuff. If I do a change mod, or if I create a new directory or move a directory, any of those events will always end up in the MDS journal. It also contains client session information. So anytime we have a new client connect to the MDS, it will write out to the journal the session information for that client. That's particularly important for failure recovery. The MDS needs to know all the different clients that were connected so that it can make sure that those clients, reacquire their caps and reestablish state with the MDS. The MDS will also move on from the state of waiting for the clients to reconnect once it knows that all the clients have connected. So it's also important that to improve the time for MDS failure recovery, that the MDS knows when all the clients have actually reconnected. Which is something you can compare to, say, like NFS, where it has to wait for the full grace period whenever it does a failover because it doesn't know which clients were connected. We also have the export-import state. So as part of moving subtrees around in the between MDSs, the MDS has to journal state several times so that it knows who's authoritative for a given subtree. We also have the purge state synchronization bits. So the purge queue operates somewhat independently from the MDS journal, but there's periodically certain events that need to be journaled so that they're in sync. And then finally, this is the big one, especially recently, is the subtree map. Every time the MDS writes out a new journal segment, get into journal segments in a bit, it needs to write out the subtree map. It also writes out the subtree map whenever it changes. And then formally, it also logged which files are opened by clients. That was actually something that was recently changed by Zhang. 2 or 3 years ago, he added the new open file table. And that was to improve MDS failover times and was mostly MDS failover times, and to reduce the size of the MDS journal. If you had a large number of clients and they had a large number of files opened, the MDS would spend a lot of time logging to its journal what files were being opened by clients, and so that was all moved out into a separate set of objects to reduce the load on the journal. Okay, so the MDS journal is as a data structure is important for the MDS because it's a way to do serial writes to a conceptually large object on top of the distributed data store that is Ceph. So obviously Ceph has, you can have billions of objects and they can be scattered all over the OSDs. But actually, knowing which objects to read and write from is just something you have to code up, and the journal represents that. The journal is in a lot of ways a circular buffer. It does occupy a finite set of potential objects, and the reads and writes go to a certain subset of those objects, and the journal is constantly growing towards the end, and then the trimming is constantly catching up with it. And all of that is managed in a separate bit of code in the objects storage device cacher library that we'll get into in a moment, which handles all of that, handles all the details of that data structure. So the MDS Journal also, especially if you read some of the academic literature associated with Ceph, the MDS Journal behaves very similar to, or I should say that the genesis of the idea of the journal was, began with the log structured file system. So if you want to learn about journaling file systems, you would look back to that old paper, log structured file systems. And, as things move forward, especially with I believe it was ext3, that evolved into an idea of we'll have all the file system state stored in regular data structures like B-trees or whatever, and then have a separate journal for actually making for making sure data is durable and also to allow for recovery. The MDS follows that philosophy. The directories are stored in individual objects on Rados, and we store all the directory hierarchy state in those objects. But we also have the MDS journal, which provides that the fault tolerance and the ability to do failover, but also it provides a hot cache for the MDS that's taking over, so that it can load all the most recently used metadata by the clients and get its cache hot when it finally turns active. So that's its other function. All right. Any questions about the MDS journal so far? Okay. So let's move on to how it's structured. So again, I said that the MDS journal goes out to a series of objects. And you can kind of think of it as like a circular buffer, but only part of the buffer is ever allocated on disk. We have an individual log object, which is, at least for the MDS journal, we're just using the blob store. And it stores a number of logical data structures. We call them journal segments. And the MDS only ever writes out an entire segment. And each segment is a set of log events that have been grouped together. And whenever you do any time the MDS must flush the journal, maybe the client requested a sync or someone executed the flush journal command on the MDS, or some locking logic between multiple MDSs require that a sync occur, that will cause the journal segment to be written out and complete with all the outstanding log events. Log events is a parent data structure or a parent class to a number of different types of events that the MDS will actually write out. We'll get into those later. There's no minimum number of log events that need to be written out by the MDS, but it always tries to delay writing out the journal segment as long as possible. There's a periodic 5-second sync in MDS, so eventually metadata does become durable, even if the load is extremely light on MDS. And once the log object becomes full of journal segments, typically I believe it's 4 megabytes is the target size for an object for the log. it'll move on to the next log object. And that's all there is to say about that. All right, and then as far as where the journal is laid out on Rados, we have this concept of what's called a journal pointer. And it's actually a fairly new concept in CephFS. It was added in about 2014 by John Spray. For those of you who don't know John Spray, he was the previous team lead for CephFS back in 2015 to 2017. And he's been working on Ceph and CephFS for a while at the time. So the journal pointer was added I'll get into that later. But the journal pointer is just a pointer to where the current the MDS journal is. And the reason it exists is to facilitate doing things like disaster recovery on the journal. If you need to write out a new journal, you want to set up a new series of objects that the MDS should write its journal out to. Well, the journal pointer exists to atomically update where the MDS journal is. And kind of think of it as a double pointer. It always exists at this object location 400, and that is which looks a lot like a regular inode number or directory inode number. For those of you who have looked at the Rados layout, on-disk layout for CephFS directories, but it's really just a static object. And in the xadder information for that object, you can find the current journal. So it'll point to the current journal head. For most Ceph installs, especially in new installs, that journal head would be at 200. And if you just run a vstar cluster and you look at all the objects in the metadata pool, you would see the MDS journal at this location. However, it can also be put in a different location. And we'll see for the long-running cluster, it's actually at the 300 location. So this would be 300. And so when the MDS is, if you're doing some kind of recovery event or for reformatting the journal, which has happened in the past, the journal pointer would be updated, and then you might just have that's all you ever see. As far as the actual on-disk information is stored with the journal pointer, it's extremely simple. You can use this Rados command line shell command to actually read the journal pointer, and it's just these two fields, the front and the back. And the front is corresponds to OX300. And this is actually coming from the long-running cluster. So this is REC0001. And you see we got the, I said the xadder. It's actually stored in the blob of the 400 object. And here we're importing it into the journal pointer type and decoding it as JSON. And so again, we can see that it's at OX300. So the long-running cluster is actually, as its name would suggest, been around for a very long time. We've been constantly upgrading it, and it's served as a nice way to catch bugs that may occur with legacy data structures that may exist anywhere on in Ceph, either in the OSD maps or in the monitor stores or on the OSDs themselves, or legacy MDS structures which may exist somewhere on some directory in CephFS. So this cluster has been around for a very long time. It's survived like journal reformattings and whatnot. So you can see, unlike a newer cluster with like vstart, you can see that its journal head is actually at OS 300, which is, if you went looking there for the journal on the long running cluster, thinking it was in the 200s, you'd be surprised it's not there. All right, and then the journal header. So I said that the journal pointer acts like a double pointer. So if you look back here, we have the 200s and the potentially 300. I put question marks there. It could be somewhere else. This log head structure tells the object cacher journaler information about the journal. In particular, where the journal objects are, as it is a large circular buffer logically, but only a subset of the objects of that buffer are actually physically present. And so there's millions of different objects that could be in that set of objects, and only some of them are used, so you need to know where they are. So in this head object, which we can get, and then pipe that into the Ceph decoder and get the journal header, you can see all the different fields here about the location of the journal objects. And the three important ones are here: the write position, the expire position, and the trim position. And we'll get into those in the next slide. There's also a layout. This is using the same logic that the CephFS library uses when it uses the OSDC library, again, to handle the filer logic concerning where to actually store the file data objects for a file. Namely, what's the stripe size, what's the object size, which pool ID, what pool namespace. All of that is stored in the layout. And the MDS Journal uses the same information to lay out its journal. But it's not particularly interesting because we're just using the defaults, which would be a 4 megabyte object size and a 4 megabyte stripe unit, and only a stripe unit of 1. So we're not doing anything fancy here. All right. So what are the write position, expire position, and all that? So the write position is where the MDS Journal is writing the latest changes to the journal. So it's going to point to the current log object that's being written to. Similarly, the expire position is noting where the MDS has expired journal segments, meaning, so what's an expired journal segment? That's a segment that the MDS has made durable by writing all of the metadata mutations for that journal segment out to the physical directory objects. So for example, if I create a file in a directory and that event is noted in one of these log objects that I want to expire, I have to go out to the directory object for that, for containing that file, and actually create the file inode in that directory object's OMAP. And then once that's complete, then that log segment is eligible to be expired. And once all the log segments in a log object have been expired, then I can adjust the expire position of the MDS journal. Now, just because a log object becomes expired doesn't mean you necessarily want to get rid of it. Because remember, I said that the MDS journal uses the MDS uses the journal to facilitate recovery. It also uses the journal for maintaining a hot cache of recent metadata. So you don't necessarily want to expire and delete everything that up to the current write position if you're expiring things as fast as you're writing. You want to keep a certain buffer of recent events so that a new MDS can get a hot cache. So the journal keeps track of where the oldest expired object is, and then it also keeps this trimmed position. So that's what we're going to use to keep track of what's actually been deleted. So there's going to be a number of objects which are trimmable and expired, and a number of objects that are expired but we don't want to yet trim, and then the current object that we're writing to. And there will actually be a group of objects which have not been expired. I didn't show here, but are complete and fully written. And then so the trim position is constantly being updated whenever the MDS Journal data structure, the OSDC Journaler, is trimming old objects, and which is really just deleting them. And then there's the expire position, which is constantly being updated as the MDS is fully writing out all the changes in the journal to the backing directory objects. So these are constantly chasing the right position. You'll also notice that if you just look at an MDS running for quite a time, and you've made a few directories or files, and you just wait for those directories to show up in Rados, you'll be waiting a very long time, because the expiring of the log object and the log segments in that object occurs only as needed as the MDS journal grows. And so those directory objects may not be created until a lot of load is placed on the MDS. And if you want to actually see all of those changes flushed to disk, you have to issue a journal flush command to the MDS through the admin socket interface, or really through the CephTel interface now with Pacific and onwards. And that'll actually force all of the current log segments to be expired, meaning that all of the changes corresponding to those log segments will actually be written out to the backing directory objects. And then through some commands to the journaler interface, all those segments will also be trimmed. All right. So another way to look at the journal header is through without actually running Rados commands and then manually running the decoder, is to also just run the CephFS journal tool. I said this was new. It's relatively new. It was done in 2014, again by John Spray. He added this tool to allow us to do some kind of disaster recovery for the journal, but also just to inspect its contents. And so this is a good tool to become familiar with as a CephFS developer, to just learn how the MDS journal works, and also be able to learn more about certain types of recovery situations. Fairly common, especially in community clusters, that something really goes wrong, and if it's really bad, they may end up doing a full journal reset, which is just wiping out all of the latest, all of the journal of the MDS and creating a new one. So whatever they have that's been expired from the journal onto the metadata pool is what they get. That's all they have. And so again, this shows you all correct. See now that, and yeah. So again, this is from a V-star cluster, and so we can see the right position is just a little bit ahead of the expired trim position. These two actually have not been updated yet, because nothing's been expired or flushed from the V-star clusters journal. You can also use the CephFS journal tool to look through the different types of events that are in the journal. So here we can do an event get list. I'm just looking at the latest 15 journal entries. And you can see we're written out a subtree map. Subtree map test is something you only see in V-star clusters usually. new session information, make DIRs, cap updates, those types of things. And you can actually, I have that in the next slide. You can see you can do a lot of fancy filtering if you are only wanting to look at the events associated with like a particular inode. You can do that with this selector. You can look at particular paths or fragments, so directory fragments, or if you just want to see everything that a client's been doing, you can have a selector for that as well. Here is the reset command I was talking about earlier. So this will allow you to just do a full wipe of the MDS journal, and this is only done during certain disaster recovery if the journal has gotten corrupt for some reason, an upgrade went horrible, be all sorts of reasons. Though generally it really should not ever be done. But you'll also notice that community members, when they become desperate, they often run this this reset command. So it unfortunately is fairly common to see in mailing list posts. And then there's these import and export, so you can actually import and export the full journal out to a file. So that's, I was going to move on to the code, but before I do that, is there any questions so far? No questions. All right. I'm going to switch to a different show. All right. So I have in the slides, you're following along on the Google's Drive link I sent. You know which code we're going to look at, but I can't display both at the same time, so we'll just look at the code on or in the screen share. Okay, so starting with OSDC Journaler. So this is all the code that handles the data structure logic of the journaler. There's nothing MDS specific in this library. And again, it's used by both the CephFS client library and also the MDS, which should make sense because both actually need to understand how to manipulate the data objects for the files. Now, if you're just in the top level source tree, you might think, you might be looking around for a journal and you find this and you think that's where the MDS journal is. But that's actually not where it is. This is code used by RBD, and nothing in CephFS uses it. So just be aware of that. The MDS journal is actually here, this journaler class. All right. So this is actually a really important comment. If you ever have to dig into this journaler code, strongly suggest you fully understand this comment before doing anything. And the main point, just to summarize what it talks about, is that the current trim position, the current expire position, the current write position are actually not updated synchronously with whatever the current write object is or expire object. It's actually written periodically out by the journaler. The journaler just assumes that these are moderately out of date, and it'll actually continue looking forward a few objects until it finds whatever the latest written object is and whatever the latest trimmed object is, and so on. And so whatever the head object says is the current write position, if you were doing manual debugging, it may not actually be that object. It could be a few objects later. So that's just something to be aware of. So I'm not going to actually go through this code much. It's just a data structure. Again, it's a logical circular buffer. with only a subset of the objects actually allocated, and there's not a lot to say about it. This code, the code for the journaler, reuses a lot of code elsewhere, data structure code, notably the filer. That's why it's in this particular library and not something completely separate. But if there's any questions about this, I'll pause here. Okay, move on. Oh, is the font large enough? I didn't hear any complaining, so I just assume it is.
Yeah, it looks good.
Okay. All right, so here's the journal pointer object. Again, it's basically a double pointer. There's not really a lot to say about it. There's the front and the back links for which journal we're accessing, and during a recovery situation, there may be two. But generally, on a stable cluster, the back link will be null, and only the front one is the current journal. So there's not really a lot to say about this. All right, let's move on to the meat and potatoes. So here is the MD log, which is the set of code that manages writing out all of the journal events for the MDS and interfaces with the OSDC Journaler. So the important bits here are just create. So here we're just creating an empty log. This is done by when the MDS is starting up for the first time, and opening the MDS log and performing any kind of replay. Let's see what else is. This is the pending event. So this is a structure we're going to see later on. Whenever the MDS needs to write out a log event, it's going to create a pending event structure and throw that in a queue. During the design of the MD log is that there's a thread for actually doing the writes out to the journaler, and there's the other threads that come in and try to create events. There'll be several different MDS threads that could do that. And so they create this pending event object, which gets thrown in the queue, and the submit thread just regularly reads these off the queue and writes out the log events. There's not a lot else to say about the header. Move on to the code. So here's creating an empty log. This is the MDS inode log offset. So the inode number for the journaler is, for new cluster will be like OX200. So that's what this log offset is. And then you actually add the node ID, which is really the rank, the MDS. So for rank 0, it's just adding 0. So that's why the rank 0 MDS journal is at OX200. And if you were rank 1, it'd be OX201. And so on. And there's actually a maximum number of MDS ranks, which is not something we often see in the wild, of 256, which is kind of, there's no real reason we have to have that limit other than certain on-disk metadata structures assume that there's only 256 ranks. Because once you add 256 to OX200, you get OX300, and that could be like a recovery journal or something. So that's one of the reasons why that limit exists. There's a bit of a diversion. So here we're actually creating the journaler metadata pool, for example, with the OX200 file object. And we're setting just another creating a journal pointer that points to that inode, saving it out, and then we just wait for all of that to complete. Right, and here's that writing the head object. Right, submit thread entry. So this is the main method that most of the other MDS code will be calling. So this is when we are going to submit a log event to the current journal segment. And actually the journal segment's already been associated with the log event by this point. For certain some structural reasons of associating a certain state with the log events. And here the code will be creating one of these pending events that I talked about earlier. And this is really just the log event itself and then the completion here. So this is a context, Ceph context, which is how we do our continuations within CephFS or in MDS. So when this actually becomes durable, this context completion will get completed. And that would result in, for example, in telling the client that the request is now fully durable, and it would get a safe reply from the MDS indicating that request is now durable. Here. So here you can see some of the logic for like when we're going to start a new segment. So here we have, like, for example, there's a maximum number of log events per segment, or if the log segment's period or size is starting to exceed the size of the backing objects, then we're going to start a new segment, and we're going to end up writing out the current one. And here is that logs our subtree map test that I mentioned earlier. So this is only done when we have this MDS debug subtrees config turned on, and then we'll actually write out the subtree map tests. And this is just as the comment indicates, just to catch replay bugs, but that's not an event you normally see. So again, that gets put in a pending queue, and you can see so this is a helper method, but actually if we looked at you can see there's a submit entry submit mutex that is guarding this queue. And here we're adding so this is just the important bit, adding that to the pending event list. So move on to hit thread. So this is the thread that's just sitting in the MDS, constantly reading pending events from the queue and writing out the log segments as they become complete. So let's see. So while MDS is not stopping, we're going to be continually running this thread. Grabbing an event off the pending events queue. If it's empty, we're going to wait for it to get an event. And here we read the pending event data, and then we check if there's a log event associated with it. There's not always going to be a log event. Sometimes you're just waiting for a flush. And here we're going to get the current write position of the journaler, associate that with the log segment, which I believe is mostly for debugging. And then finally, here's where we're actually appending the buffer list containing the log segment out to the journaler. And then you wait for the journaler to flush. Once that's completed, you'll run this finisher. And now that I'm looking for it, I can't find it. Anyways, as this actually is flushed, there's this is a continuation you'll often see in the MDS logs. If you look at a debug log, you'll see lots of these. And it actually is just a wrapper for completing another context, which would come from another part of the MDS that wants to know that something has become durable, but also records the current write position. And there'll be a number of these for every log event. So you can see this was created with the data.fin. And again, the data object is just the pending event that we read off the queue. And the fin is the finalizer associated with it, the continuation that the MDS is going to run when the log event becomes durable. Yeah, so that's just a submit thread. It's just looping on those and reading pending events and writing them out. Any questions so far? So starting a new segment is something we do when we want to force certain events prior to that segment to be flushed or expired. This is something you might see, for example, when we're telling the MDS to flush its journal. In order to do that, we need to fully flush its journal, we need to tell it to start a new log segment so that all the previous events in the prior segment can actually be eligible for expiration. So that's one of the circumstances where you might have this starting a new log segment. And generally, it's not something you need to think about when you're interacting with the MD journal. But important thing here is preparing a new segment. So here is where we actually allocate a brand new log segment within the current event sequence, which is just keeping track of the number of events that have gone through the MDS. And here, tree. Oh, now that I'm looking for it, I can't remember where I put this. And then create. there it is. So that's what I was looking for. So here's where we actually here it is. So we actually create the new segment, and then the first thing the MD log does whenever it creates a new segment is it creates a new subtree map object event. Sorry, subtree map event. And every time the MDS starts a new journal segment, it actually writes out the subtree map. And that's done here. So it's actually going to ask the metadata cache to create the subtree map, which is just a special event in the MDS journal that records the entire subtree map as of that current point in time, and writes that as the first entry associated with that journal segment. And this is done to simplify data recovery during MDS failover. And the reason I bring this up is that, especially if you're looking into performance issues, right now one quirk of the MDS is that if you have hundreds of subtrees, that subtree map can get extremely large. And that means that every time the MDS is preparing a new journal segment, it actually will have this gigantic subtree map taking up space. And the MDS journal is just spending a ton of time writing out the subtree map. And also acquiring the metadata server lock, big lock, in order to do that. So it's very expensive. This is actually motivation for one of Jung's recent changes he had done before he left, which he actually just renewed the pull request a week or two ago to pull the subtree map out of the MDS journal. And that is, it's all centered around fixing this bit of code, which is writing out the subtree map segment. And again, the reason for doing that is to handle those scalability issues. All right, move on to recovery thread. So this is called when MDS is doing replay. This might have to be the last thing we talk about because already 10 minutes till top of the hour. I wanted to leave some time for some QA. So here we have the recovery thread for the MDS, or the metadata log. And here this is really just going through the different events for the MDS journal and reading them off the disk, reading them off the metadata pool. So here we're loading the journal pointer behind the current journal. Generally, is we're just going to be so here's the back journal. So if we're doing some kind of reformatting of the journal, or there was a journal reset, this might be non-null, but generally it will be null. And if it is null, then we're going to just load the journaler with the front object of the journal pointer. And here we're going to recover it. And so the recovering is, this is the OSDC Journaler class method to recover the journal. And that's just, again, remember that the journal head may be out of date, so we're asking the journaler class to load the current write position and fire position and figure out where the actual latest write position is. That's what the journal recovery there is doing. And once that's done, we figured out what the actual write position, trim position, expire position are. Write handlers. There's even a case to reformat. And then once that's done, we can actually do replay. So here, the error handling. And then here in the replay thread is where we actually are going to, and this is called by, if we're in standby replay or if the MDS is in the replay state, it's actually going to read the events off the journal, decode the event here, And and then here actually we do the replay of the event. And that's just taking the updates out of the log event, creating a directory or whatever, and applying it to the metadata cache. And so that allows the MDS to rebuild the metadata cache whenever it's replaying events off the journal. Okay, so I think I ran out of time. I'm going to leave a little bit of time for Q&A. We can talk about the other parts of the metadata journal sometime in the future again. So open the floor. Any questions or comments about what I've gone through so far?
Patrick, as a CephFS admin, when do you typically do a journal flush?
You don't ever really need to. And as part of journal flushing, it might trim the journal. You might do it if you need to do some kind of recovery and you want to make sure that everything's currently in the journal is written out. But generally, you would probably be doing that recovery manually with the recovered entries option to the CephFS journal tool prior to perhaps deleting the journal through a reset command. I do a lot of journal flushes just because I want to perhaps manipulate the directory objects, or I want to ensure that everything is synced out. But yeah, there's not, as an admin, there's not really a lot of reasons to do it. Oh, if you want to drop the MDS cache, probably want to flush the journal first. In fact, actually the flushing the MDS cache, or sorry, dropping the MDS cache, that code in the MDS actually flushes the journal too. And that's necessary because you need to expire everything in the MDS journal so that a lot of the metadata in the MDS cache becomes unpinned and eligible to be dropped. If you don't flush it, then the MDS may not drop anything. You have hundreds of megabytes of cache that just is not actually dropped. The MDS, a little bit divergent, but the MDS dropping the cache was an interesting idea as part of doing performance tests, but due to how slowly you have to drop the cache in order to prevent destabilizing the MDS, it's not very useful in practice, I find. But that, at least for a performance perspective, if you're doing tests, you're better off just recreating the file system because it just takes too long to do it in a safe way. But I don't think dropping cache has become very common in for community admins, so you don't see it there very often. I mean, I don't hear it talked about on the mailing list, and that's really the only way I would know. Did I answer your question, Ramona?
Yeah, that makes sense.
Okay.
Seems like when you want to drop the cache, that's when you want to do it.
So Coach asked, what's the average size of CephFS journal in comparison to the data stored? So I was just read the numbers for this, but the MDS journal I think can get to a few hundred megabytes in size, but it tries to cap itself around that size by forcing trimming. The metadata pool, of course, can get as large as needed, but it usually just ends up being several gigabytes because the metadata just simply doesn't take up that much space.
And Patrick, can you talk a bit more about the optimization regarding the subtree map? able to follow that. What's the issue and what has Jung been trying to solve in regards to the subtree map that is being stored in the journal?
So again, this is something you only see if there's a lot of subtrees in CephFS. It was never really a problem that was noted, at least in the early designs of CephFS. Like, you won't see it talked about in the early CephFS papers. The dynamic balancer does not generally create very many subtrees. You might get like a dozen on each MDS. So that's not a scaling problem by itself, but or at that level. But once we added ephemeral pinning, where you can have a number of subtrees created according to whatever the size of the directory is, at least especially with distributed subtree pinning, which at least the first iteration of the design of distributed ephemeral pinning, we had a subtree for every subdirectory under a directory. So think the canonical case I always mention is the home directory. So we want every user's home directory to be pinned to a particular MDS through ephemeral pinning. So you would have a subtree for every home directory, which, obviously you could have hundreds, thousands, and that did not. We had scaling issues. The rank 0 would be, which was authoritative for the home directory, would be overloaded with journaling. It's slow to respond to lock requests. It just was. We suddenly found out that this was actually a scalability issue. The initial idea was to somehow figure out how to stop writing out the subtree map every time we do a journal segment. Is there some clever way we can reconstruct the subtree map while reading the journal? Jung ultimately didn't elect to do that. He pulled the subtree map out of the MDS journal completely. I have not actually dug into that part of his PR yet, as far as where he's storing the subtree map now. It might just be a separate journal. Which reminds me, I mentioned I was going to talk about the purge queue. Purging was originally part of the MDS journal. I have a little bit of time. I'll just mention that, like the MDS would periodically, when an unlink event was going to be expired, it would actually delete the corresponding entry from whatever directory object held the link. That was low-hanging fruit to improve the performance of the MDS, because deleting directory trees is fairly common, and it doesn't necessarily need to be done immediately during event expiration. So the purge queue within the MDS exists to handle the logic of actually deleting files and truncating files and certain other truncating and deleting files, and also stray reintegration outside of the journal machinery of the MDS. So the purge queue actually maintains its own separate journal, same journaler class, for all the files that need to be deleted. And it does that out of band of the MDS journal. So this is kind of continuing a trend of splitting things out of the MDS journal, because it's become a full large data structure that takes too long or it doesn't scale very well, all the different things that the MDS actually needs to do. So the subtree map is now the new victim to remove out of the subtree, or out of the MDS journal. As far as whether or not we will merge Jung's PR, I have to go through it still, and I'm not exactly sure whether it'll be the right approach, but I generally trust Jung to make good choices in that regard, so it'll probably be merged, especially since apparently he's still working on CephFS. I wasn't sure if he'd be around to clean up any bugs that may surface with the result of merging his PR, so we'll see about that. Anything else? Any other questions? So just to kind of close this topic out, I think what we will find going forward is that the MDS journal, there'll probably be other things we want to pull out of it. As far as making the MDS faster, it's anything we can pull out of the journal into a separate thread and data structure will probably end up being a large performance improvement for the MDS. So that's something to consider in future work for CephFS. One example of that is the recursive unlink RPC that we want to implement, where we no longer journal or have a number of RPCs with the client and a number of journal events associated with deleting the directory tree. That could be something we potentially pull out into the purge queue. And then as another example, again, I mentioned that every time we have a new client, we write that out to the journal. If we ever get to a situation where we have thousands or tens of thousands of clients in MDS, we have no idea what scaling issues exist at that point. And we may need to rethink how we journal client sessions out in MDS in that particular situation, but I don't think we're anywhere close to that yet. All right, I think we're out of time. Thanks, folks, for showing up, and see you tomorrow.